So no TVAC results in this. Everything here was computed a couple years before TVAC, but hopefully still interesting. So I'll talk about the observing scenario time series modeling. Basically, everything talked about in here is described in detail in this paper from last year in Day2. So want some details, please read this. Okay, so why do we need a time series modeling? Two basic reasons. First, evaluate post-processing techniques. Our speckles, even after digging the dark hole, are going to be as bright or brighter than planets we want to see. So we have to use post-processing, some sort of PSF subtraction technique to get rid of them. And that's dependent on the stability of the telescope and the chronograph. And we want to see how well our post-processing techniques work on images that show variations over time. For baselining, classical reference differential imaging, we've also got angular differential imaging. And then we also want to test the more advanced algorithms like CLIP that basically optimize these subtraction methods. Then we also want to verify the CGI error budget, and Brian will be talking about that in the next talk. The error budget is basically the analytical description of the system that provides insight statistically into how the contrast will vary over time given certain perturbations and how that affects our performance requirements, specifically the flux ratio and noise requirement. So the time series includes a number of different models. So we've got the diffraction model, and there's also diffraction modeling done in the LOFUS model as well. So this is computing the dark hole by propagating the wavefront through a system using Fresnel techniques such as angular spectrum and Fourier techniques such as angular spectrum and Fresnel. And we have STOP modeling. STOP stands for structural, thermal, and optical performance. And this is where we're doing the finite element model, the thermal and structural modeling to get the structural deformations. And then we use ray tracing to derive what the wavefront changes are from those structural deformations, along with optical misalignments. And then there's dynamics model. Alon talked about this yesterday. This is where we look at the structural perturbations that are induced by the reaction wheel vibrations as we speed them up and down as we slew and roll the telescope. And the primary effect of that is pointing jitter. So the diffraction model gives us our two-dimensional image filled with speckles. It's what we run our dark hole digging algorithms on. And the stop and pointing model is telling us what the perturbations in the system are that we feed into our diffraction model. So in our diffraction model, we represent the entire optical system. So every optic has, and there's almost 30 elements here. So every optic has either a synthetic or measured fabrication error. We also include polarization-dependent aberrations that are computed from ray tracing that incorporate the coding properties. We have a deformable mirror model, and then representations of the mask. And we use the wavefront propagator to go from surface to surface to surface. And we do this monochromatically, and then to create a broadband image, we combine monochromatic images. And to incorporate the polarization aberrations, we have to compute at each monochromatic wavelength 4 separate polarization components and add those together as well. So there's a whole lot of Fourier transforms going on just to create a single image. Now, in our diffraction model, we apply the same sort of wavefront control techniques that we used in thermal vac and that we'll use on orbit. Before we do any wavefront control, we've got 10⁻³ contrast in our dark hole. Then we do flattening, as AJ and David described yesterday, where we flatten the phase. And then we insert our masks, and then we run electric field conjugation to dig our dark hole. Now, once we get our final dark hole, this is the starting point for our time series modeling. We now want to know, how is this dark hole, how are the speckles in this dark hole going to change over time? It's where the stop modeling comes in. The primary input to the stop modeling is the observing sequence. This tells us where we're pointing and when. That gives us our how much do we have to change the reaction wheels, and where is the sun pointing on a spacecraft. And since we're doing RDI as our baseline, we've got a bright reference star to do our reference image. And then of course we have our target star. So we start off by observing the bright reference star. Now we assume that at some time previously we've dug our dark hole, and now that we're doing our science observations, some time has passed, so we need to kind of refresh our dark hole. So we spend a few iterations of EFC kind of restoring our dark hole. And then we take about an hour's worth of reference images. And we slew the telescope to our target. And now we want to also be able to implement on our target angular differential imaging. So now we roll the telescope back and forth a couple times to the target. So the planet moves while the speckles do not. This rotisserie helps. This rolling back and forth helps because it kind of rotisseries the telescope so that we aren't staying a long time at one position, just kind of building up heat at one position of the telescope and increasing our drift. And then we go back to our reference star and take another image. Now, doing it this way, this is a way we've come up with. This is not like the predetermined, this is how we're going to do it. But by doing it this way, this allows us to create an interval where our wavefront stability requirement is spec'd at a 10-hour time scale. If we instead did a bunch of reference images, then days worth of target images and all that stuff, our requirement would have had to span that entire time. But now it's just spanning 10 hours. However, we can then stack these cycles one after the other to increase our integration time while maintaining that strict 10-hour requirement. And then if we have some long-term drifts, we can insert like an iteration of EFC in the middle to refresh our dark hole. Spoilers, OS 11 was stable enough that I didn't need to do this refresh. But there is, you do have to acquire images and send them to the GoFund and send up the DM commands and all that stuff. But that wasn't included. That particular step wasn't included in the simulations I do. So you can just keep stacking these as much as you need to get integration. And if you're doing spectroscopy, you can need days and days and days of this. So the observing sequence tells you where you're pointing and when. That gives you your solar angles. We selected 2 real stars for these simulations. The target and reference star are separated by, I think, like 100 degrees on the sky. But in terms of solar pitch, they're only about 3.5 degrees. We previously ran earlier a model where we had a different reference star that was 15 degrees solar pitch, and the aberration changes were huge beyond what we could tolerate. Um, the observing sequence also tells us when we need to change filters and when we need to move mechanisms and run the DMs and do calculations within CGI. So that tells us what our internal CGI heating sources will be and when that's happening. And then, as you saw yesterday, the slews and rolls, we have to tailor a sequence of reaction wheel speeds that meet that. And so we've got that included as well. One of the downsides of this multiple cycles is that there's a lot of time spent going back and forth, slowing and rolling. So there's some inefficiencies built into that because it takes about 30 minutes to roll, to slew, and about 15 minutes to roll. So this is a layout of the modeling steps that we go through. So we've got our observing scenario times and orientations. That gives us our solar angles that go into our finite element model. Also gives us what we need the reaction wheel speeds to be for our slews and rolls. And also then it gives us what our CGI power profile is for our internal heating. Finite element model, so we do stop modeling using standard software. So thermal desktop for thermal changes, then Nastran for the resulting structural deformations, then SIGFID and Code 5 to do the ray tracing to get our wavefront changes and our optical alignment changes. And so the wavefront and alignment changes go into our diffraction model. The wavefront changes are also sent to the LOFUS model. And so LOFUS computes what a measurement, including all the system noise, such as detector noise, and sends those to the diffraction model. So the diffraction model has inputs, the wavefront changes within the diffraction model can move the focus corrector mechanism and move DM1 based on what LOFUS tells us to do. In parallel, we've got the dynamics model, which gives us our pointing errors. We don't run that through the explicit LOFUS model. Instead, it's a filter function applied to the PSDs of the vibrations, the induced vibrations. And that in it includes the corrections that the fast steering mirror will provide. So those go into the diffraction model as well. So we have to do this for every time step spanning observing scenario. For OS 11, computed 1,800 time steps. And then those images, so we create a data cube of images, and those could be interpolation sample to finer sampling. And then those, you can take those and push those through a detector model and do your photon counting to get your final images. This takes a long time. Just the thermal modeling in the stop model takes over 2 weeks. Fortunately, thermal modeling doesn't parallelize well, so having a supercomputer doesn't help you too much with that. We do apply some modeling uncertainty factors. So in the dynamics model, factor of 3 to 10 based on frequency. In the structural model, all deformations are multiplied by 2. So that also means that the wavefront errors and optical misalignments are also increased over what the model really predicts. This is the low order aberrations before correction, well, some of them. As you can see here, the variations are low. We're getting only a few tens of picometers RMS over this entire time span. You can see that there's a strong correlation with the roll of the telescope back and forth, creating this sawtooth pattern. Now, What we're seeing here in red are again those same stop model predicted aberrations for Z4 through Z11. And then in black is the difference between those aberrations and what LOFUS, the LOFUS model measured. Now it looks like it's a bunch of kind of noisy trash, but it's not. One thing, the LOFUS model was tuned to the requirements variations in the aberrations, which are much higher than what we predicted. So we can tune LOFUS better to match these levels of aberration changes by increasing the bandwidth, the temporal bandwidth. Did not do that in this case. So this is kind of requirements level LOFUS. But it still does something, as I'll show later. You can see, and then of course, if you need to integrate all this over the time of integration. So once you average these out, you actually do see some advantage to this. Some things like trefoil and spherical, obviously LOFUS did more harm than good, but we can tell LOFUS to just correct those if we need it. Also, here's the pointing jitter. As you can see, we've got spikes that go up to over like 1.5 milliarc seconds RMS right after the slews as the reaction wheels are spinning down. But most of the time, we're at about 0.4 milliarc seconds RMS. So here's the taking all the images and just putting them into a time series without detector noise. This is the OS11 time series for HLC. And you can see these variations. In some cases, you see kind of sudden little brightenings, and that's where the jitter's high after the slews. But in most cases, most of the variations you're seeing are on the order of 1 or 2 times 10 to the minus 10 level. The dark hole contrast here, I think, is something like 3 times 10 to the minus 9. Most of those residuals are probably uncorrected coma. The chronograph is especially sensitive to coma. You can see if I take all those images, if I take the target star images together and put in planets, and then take the reference star images and add noise and do just the simple differencing, I can see planets 2 or 5 times 10 to the minus 9 in the simple subtraction. We do the same thing for the other baseline modes: shape pupil, wide field of view, shape pupil, spectroscopic mode. For spectroscopic mode, each time step also includes monochromatic PSFs versus wavelength. So it's a stack of about 30 to 31 wavelengths. And shown here are 3 sample speckle spectra to show you the chromatic variation. And then the little error bars are how much at that wavelength the intensity changes over the course of OS11. So Marie Goof and collaborators have taken the simulations and run post-processing analyses on these to see how well the post-processing algorithms do. I ran 2 simulations, one called no muffs and one with muffs. These all have the structural and pointing error muffs. But then with muffs, I also increase our sensitivity to pointing jitter by a factor of 2, just adding a little certainty in there. And then they analyzed cases without detector noise and with detector noise. And our reference here is classical RDI subtraction. So what they did was, what was really interesting is seeing what the advanced algorithms like CLIP do, how much of an advantage they have over just the classical subtraction methods. And here the FAC number, that's the factor of improvement over classical subtraction. And you can see they vary by up to about an improvement, a factor of 2 over classical. The more stable your system is, the less advantage you're going to get from these advanced algorithms. If your system's perfectly stable, they won't provide any advantage. Classical subtraction will do as well. And then adding detector noise kind of pollutes your images that you use to derive your optimal sets of modes. So, we have low signal, so we're much more stable, and we have low signal. So, things like HST or on the ground or something where you apply clip, much larger factors of improvement. Here, because we're much more stable, we don't get as much of an advantage. All right, so in summary, our OS11 simulations are showing that speckle stability, we've got brief periods, it's dominated by jitter after the slews. Otherwise, it's probably residual coma, which is role dependent. And we can improve this by tuning the locus. Advanced post-processing techniques like clip, providing about a factor of 2 improvement over classical RDI. But the more unstable the system, the greater improvement factor. So if these are predictions are too optimistic, then it's likely that things like clip will actually give us a larger improvement. In a previous observing scenario, we verified the error budget. Maybe Brian will mention that. These time series images for these 3 modes are available on the IPAC website, and for this and for earlier scenarios, so you can grab them. And then it's a question, is a revised OS11 coming? So the thermal models, the finite element models have been continually tweaked since the 2 years or so that we did these simulations. And so there's talk of maybe rerunning those, and in which case we could run a new time series, speckle time series, and maybe incorporate a better tuned LOFUS as well. Then maybe run one case with a higher contrast, like a 3 times 10⁻⁸ contrast that matches what we got in ThermalVac, in which case we'll have much higher sensitivities to aberration changes. And in that case, things like clip may show a much better improvement, though maybe tuning LOFUS better will also reduce the effect of those increased aberration changes. And that's it. Thanks.
Thinking about a revised time series prompts me to just comment that we're doing some optical model validation work on the telescope and the TVAC test that's like about to happen. So that might be a useful input if you're going to go through all that work of rerunning models. I don't know when we would have those data in a usable form, but it's worth a thought.
So I didn't quite follow that.
So we're going to have an updated stop model of the telescope based on lab measurements coming out of TVAC. And so that might be incorporating these results.
It's a great idea. So we are coordinating with Alice, might be online. Right now there is a cycle 4 for the entire observatory. It will include correlated thermal models with WFI and CGI, but I don't think anything else yet. That would wait for cycle 5. So, so there's several flavors of changes. One is that internally our thermal operation will change a little bit. The color fault protection will turn off some slices, introducing some additional disturbances. So we're rolling into OS11 update. then the observatory model, we can use the cycle 4 model going forward. And also we may, think about how to optimize when running the reaction wheel, which is in discussion with Alice, maybe let them spin up more. And, there are some trades there to be made. So yeah, I agree. And then of course, when the telescope correlated thermal model becomes available, that will be another update.
It
So
takes a
we'll
lot of
coordinate
time,
with
I
observatory.
know, but it-
The short answer is yes, we will do an upgrade. Just one quick question about the downport bandwidth. You were showing all the loads. What was it on that particular case? And you're thinking we should make it longer if really the
Can you say, Brandon?
Yeah, it's 20 hertz for line of sight and 1.6 millihertz for all of the higher order modes, C4 to Z11,
600 seconds, 10 minutes?
100 seconds.
1.6 millihertz?
Control hertz versus reciprocal
Oh,
seconds.
Which of the DM like characteristics were in OS 11? Like, was the dead actuator in, or like the drift?
The measured flight characteristics, the dead actuator, the actuator coupling, the gain variations per actuator, those were included in the simulation. And for those who are interested in the model, the proper model that's used to generate these, along with Mapper CGI Sim, there's a new version coming out either this weekend or early next week that incorporates the flight DM model.
For the PSF subtraction, it looked like classical ADI did the best, which I guess I'll have to poke around and detail why it did not do as well as CLIP. But what was assumed for the astrophysical scene in that? Did you assume the star was a point source? Did you assume any exozody?
No, it's just an isolated star that did have winning jitter and had two stars were different sizes, but there was no background astrophysical scene except. Yeah, I don't know if you used versions with planets embedded or not. Yeah, you did, right? So.
So.
Do you, given all the things that you've modeled a ton and impressive, do you have any lessons learned for how you would say, well, if we did this a little differently in the hardware, that it would have been, easier or better to model or capture?
Well, there's lots of things you wish you knew. You wish you had a high order wavefront sensor, so you could get not just the low spatial frequency errors, but also the mid spatial to get changes in optical misalignments over time. Something you can easily do, and just knowing the optical, one of the big things in modeling is just characterizing your system better. A model is garbage in, garbage out. So it takes a long time, a lot of work to get measurements that we need. And some of those measurements only came out in thermal vac, which was, 2 years after we generated